Okie dokie, artichoke. We're here to learn about number systems. There are three number systems that are commonly used in everyday life and computing. So the first one is decimal. These are considered to be base 10. This means that the exponent on the base, which is 10, increases by 1 each time you go up a place value. So here you'll see you got the ones, which is 10 to the 0, the tens, which is 10 to the 1, the hundreds, which is 10 to the 2, and then you'll have thousands, 10 to the 3, and 10,000s, 10 to the 4. So the exponent increases every time the place value increases, but the base will always remain 10. And it continues on forever. So now an example, 4,734. So to split that up, in the 4 is the 3 is in the 10 spot, the 7 is in the hundreds, and the 4 is in the thousand spot. So how you take each of those pieces to get you your total number, so you have 4 times 1, which is 7, so 7 times 100, plus what's in your thousand spot, which is another 4, so 4 times 1,000. It's just breaking down the decimal number to understand like what place values it is a part of. These are our counting numbers, so you get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then it gets kind of tricky because after that you end up with 10, which is 0 and 1, and yeah, computers don't like it. So binary. These are base 2. They follow the same concept as decimal numbers, but instead of having the base of 10, it's the base of 2. Computers really like this. It works with hard drives and other basic pieces, as it is just a series of on and offs. So again, we start off with our 1 spot, but it's 2 to the 0 this time. Then 2 to the 1 for your 2s, 2 to the 2 for your 4s, 2 to the 3 for your 8s, and 2 to the 4 for your 16s. The system is entirely comprised of 1s and 0s, and it's pretty neat. So you'll see all these numbers are pretty common in storage memory capacities because it all works in binary. Okay, so here we're going to break down how to change a binary number into a decimal. So it's the same thing, you take each spot as it's in its place value. So there's nothing in the 1 spot, 0. So 0 times 1, which is 0. Then plus 1 times 2, because that's in your 2 spot. Then in your 4 spot, you have another 1, so that'll be 1 times 4. And then you're going to add on what's in your 8 spot, but there's nothing there, so it's going to be 8 times 0. And then you're going to add on 1 times 16. So when you add that, you get 22. So that 22 there is a decimal number. So to write, like to distinguish the difference between binary and decimal, there's a little subscript that has either a 2 or a 10. These, it's just zeros and ones. Okay, hexadecimal. The first two are pretty common, and while a lot of people don't know much about binary, they've still heard of it. Hexadecimal, however, isn't a piece of many's everyday knowledge. It is base 16. It follows the same pattern as the two before, but with a base of 16. This allows it to store much larger numbers and files as much smaller, more condensed forms. This system uses both numerical and alphabetical characters. It's wild. So as it increases, 16 to 0 is 1 again, and 16 to the 1 is 16. 16 to the 2 rapidly jumps up to 256, and then 16 to the 3 is 4,096. So it increases so greatly in such a short amount of time. So here you have the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you start letters. So you go capital A, B, C, D, E, and F. So each of the values of the letters increases by 1 following that 9, maxing out at 15. So an example, FA. And to show that it's hex, you put a 0x in front of it. So A is in the 1 spot, and F is in the 16 spot. So A is equivalent to 10, and then it counts up from there. So B is 11, C is 12, D is 13, E is 14, and F is 15. So you have 10 times 1 plus 15 times 16. So you're going to have 10 plus 240, which gives you 250. So that's the decimal form of hexadecimal FA. So it's taking 3-character number and putting it into 2. It's wild. So ASCII. This is really important because we need letters in computing. This is the American Standard Code of Information Interchange. It is an 8-bit code that can be used to create every letter in the English alphabet and some symbols. The English characters can be saved as a small size and is universally used in English-speaking countries. However, it's incompatible with other languages and programs. And with the 8-bit system, it has a max of 256 characters. So capital A equals 65. It's the 65th character that they have. And that's really clever because of how you write it out in binary. Lowercase a is 97. It keeps it really simple and clean. You only have to look at certain digits to know like what letter you're talking about. So in binary, A, which is 65, is represented as 0, 1, 0, 0, 0, 0, 0, 1. And then B is the same, but you switched the 1 in the last place. So then to get to your lowercase numbers, at the beginning, instead of having 0, 1, 0, you'll have 0, 1, 1. And then the last digits stay the same. Okay, next is UTF-8. So UTF-8 is the Unicode transformation format. It is a compromise of ASCII and UTF-16, encoding that can be as compact as ASCII if the file is just plain English text, but can also contain any Unicode characters with some increase in file. It was created to make international communications compatible with the development of the World Wide Web. So with the English characters, they're exactly the same as in ASCII. But then it gets more complicated with other languages. So now we're going to do some more conversions, but this time it's going to be decimal out. So decimal to hex. This is all about division, and this way you need to know your places. But if it's a smaller number, it's not that hard. So we're going to have 307. So we are going to divide. We're going to write out our places. We got them there. So 307 is between 4,096 and 256. But 256 goes into it only one time, and then you will have a remainder of 51. So then 51 is now between 256 and 16. So 16 goes into 51 3 times with a remainder of 3. So then 3 is between 16 and 1, so then 1 goes into 3 3 times. So then that gives you your hex number, 133. So 307 in decimal is 133 in hexadecimal. So now we're going to do decimal to binary. Whoa. So it's the same concept as decimal to hexadecimal, but the values of each place change, and it's much smaller. So this will be expanding out the number pretty greatly, usually with binary, because binary is a lot larger. So you have your place values there. So we're going to use the number 14. So 14 is between 16 and 8. So then 8 goes into 14 once, with a remainder of 6. So then the next value, so the next value is a 4, and 4 goes into 6 once. So then the next one is a 2, and that'll be in the 2 spot. So that goes in once. And then you have nothing left for the 1 spot, and 0 goes into 1 no times. So your binary translation for 14 in decimal is 1110. So now we're going to go from binary to hex. It seems like it'd be really complicated, but it's surprisingly easy. So with your binary number, we're going to use 11010110. So each of the 4 bits represents one hex character. So if you convert the nibble right there, those 4 bits, then that will give you the value for the hex number that you need there. So converting 1101, you're going to have 1 plus nothing plus 4 plus 8. So that's going to give you 13. So again, we're just writing out the 0 to 9 and then A, B, C, D, E, F for your hexadecimal values. So 13 in hexadecimal is the letter D. So now 0, 1, 1, 0. So you have 0 in the 1 spot, plus a 1 in the 2 spot, plus a 1 in the 4 spot, plus a 0 in the 8 spot. So then you're going to end up with 6, and 6 is just 6. So your hexadecimal conversion of 11010110 is just D6. That's it. And then converting the other way is just vice versa. Each character in hexadecimal is worth 4 bits in binary. So it's just backwards, but it's the same concept. So that's number systems. Thank you for watching. I hope this shows that I know what I'm doing, because I know what I'm doing. I'm just bad at talking.